This is the introduction to statistical inference and modeling class. This is a lecture given by Jitkomut. Okay, I'm with EE department at Chulalongkorn. Today, the introduction of this class will cover some basic concepts and the overview of the methods in this direction. We will go over the procedures, the things you need to go through when you want to learn a statistical model. Okay, and we see the detail of the listed topics in this lecture. The basic concept of statistical learning is to build a statistical model. Okay, this statistical model explains a response variable from measurement, from data. If we focus on here, okay, we will refer to the notation of the response y. The response y is some physical variable that you are interested in, and you believe that this y can be explained. Okay, this y was influenced by some input variable or some predictor. This x, okay, when it goes through a relationship, right? A relationship, and by that we mean it goes through some mathematical function fx. Okay, it had a response here. For example, okay, for example, I mean in this course, I'm going to provide a data set based on our department facilities. These are solar cell, solar power. We have we have a bunch of data set for you to learn. So you have the sun, you have irradiance, okay, and you have solar cell. All right, these solar cell generated solar power. Okay, so we have a variable I, we have variable P, we have sensor to measure these two variables. Okay, and then we also have weather station where you can observe the temperature, the temp. We can observe we can measure the relative humidity and the wind speed. Okay, all these kind of things. This is to provide how we introduce this concept. I mean, in the field of engineering, the solar power is the response variable. You want to explore, you want to explain, you want to understand the behavior of the solar power. Okay, so the response is power. But then in order to understand how much solar power is generated at a certain time, all right, of course, by the physical property, you know that solar power should depend on the solar irradiance, should depend on the weather condition, which means the predictors, the variable that explain the power, can be irradiance, can be temperature, can be relative humidity, can be the wind speed, can be some more cloud information. Because if you have cloud, right, of course the radiation that will be absorbed and the solar cell is here. So the solar irradiance that receive on the solar cell will be less if you have more cloud. Okay, in this setting, we say that solar power, the response variable, have some kind of relationship with the predictor X. And that relationship, even though you can find this X, is going to be a difficult problem because of this reason. In all kind of measurements, there are always noise corrupted to the system. So even though you have this representation exactly in a perfect way, but whenever you sense those variables in numerical values through a sensor, there's a noise corrupted. Okay. Okay. With this setting, the whole point of statistical learning is to build an approximation of fx to explain a relationship between x and y, so that in the future, whenever you measure the new values of x, for example, If I give you that the solar irradiance of tomorrow, for example, of tomorrow, if this is going to be like 600 watt per square meter, if my temp is going to be 25 Celsius, how can you use these to approximate the solar power generated tomorrow? So this is kind of a question, which means building an approximation of these relationship will allow you to answer that kind of questions. When we have a learning problem, we can have several objectives. For example, in the prediction problem, you have, so this is health data. You have patient with a heart attack. The goal is you want to predict if a patient will have the second heart attack. The data, of course, you need some kind of the clinical measurements of the patients. Okay, you need to know their diet profile. Probably you need to know some demographic profile of a patient as well. Caucasian, Asian, age, gender, those kind of things. Okay. Building a statistical model would mean how could you explain the relationship between the heart attack and these variables? Okay. I'm gonna skip to another objective, classification. This is equipped and implemented in our daily lives. All right, we have emails, right? And as you see in your email platform, there's a spam box. So there's some algorithm running inside to filter whether an email is a spam or not. Okay, so data would be, so you see that here the response, you will, the response or the variable you're interested in this application would be an outcome to classify whether an email is a spam or not. Y is 1 if the email is a spam, is 0 if an email is not a spam. But how can you decide that? An algorithm that runs behind it is built based on some kind of model, some relationship. What do you think? Of course, an email is spam or not, you know that that's gonna depends on the contents inside the email, right? The text. If the text contains something that lead you to believe that it's gonna be advertisement, so that highly regarded as a spam. Okay. So the data would also conclude into groups. The email that is relevant to a user, these are the good emails, right? And example of spam emails. Estimation problem. Okay, this is another goal. Suppose you have a population in a region. For example, you have, if you look at people who live in Bangkok, right? We have different, we have like a very diversity of people here. You want to estimate salary or the income of this population. Okay. You have rich, you have low income, we have many classes. How are those people obtain different levels of incomes? Of course, you have to think. So the Y, the variable Y, the response would be the income, the wage. I mean, of course, you believe that this is somehow related to education, all right? People who have a very high degree should get paid a lot, all right? Should depends on the year of experience, all right? If I'm in this company for 5 years compared to another guy who worked for 10 years, you think that it should depends on the working years. Does it depend on age, right? Somehow these two guys are related, age and year. Does it depend on gender? Oh, this is a very debatable question, all right? If there's some kind of indicator that says that, oh, female get paid less than male, That's going to be a social problem as well. But these kind of thing, you can have a hypothesis in your model. All right. So if we can build a model, statistical model that explain these relationship, that is a function of gender, function of age, education, and year, which means if you have a new profile of population in Bangkok, if you have someone that, okay, I am a female, I am 40 years old, I have a master degree, all right, and I've been working for 6 years, can you approximate how much I would get paid, right? You will be answer to that question if you have built a statistical model. You can also raise a question like, oh, this relationship, is gender an explained variable? Is gender a significant variable in order to explain the wage or not? Or it doesn't matter. Both male and female get paid almost equally. All right. So this kind of a question can be asked if we have a model. Last one. A problem in the last type. This is called inference. Inference means that it's not about it's not about approximate. Sorry, it's not about estimate or give you an approximation of the response variable directly, but it's a questions where you can draw some pattern, you can infer something else as a derivative from that model. For example, you have stock price, right? You have USA, you have Japan, you have Hong Kong, you have Thailand, right? Of course, you have stock prices in different countries. In the estimation or prediction problem, it would be a problem where you can predict the stock in USA in the future, right? But the inference problem, this is an example. For example, you want to explore if these kind of variable have some independent or dependent structures. Whenever the stock price in the USA dropped, does it always affect the stock in Thailand as well or not? Right? So this is not about predicting the stock price of Thailand directly, but it's more about other questions. Whenever you have the model that explains the whole system, all right, you want to infer something else, and in this example, to infer some interconnection relationship between variables. Okay. Okay, I should also display this, show these graphical examples here. This is some example of prediction, as I said before. On the x-axis, this is the value of solar irradiance, and on the y-axis is generated solar power from solar cell. The blue dots are the data points. All right. So if we can build, when we say we can build a statistical model, we mean we can explain a relationship between y and x. And in here, I use the red line, and this red line will be explained by some mathematical equation. You can argue that, okay, I use the straight line, that's a linear regression. Okay. I mean, someone else may say, I'm going to use polynomial function, doesn't have to be linear one. That's another model. Okay, so in this class, we will give you example of bunch of fx, basically. On the right half plane, sorry, on the right graph, is about forecasting problem. Stock price, the exchange rate from exchange rate between Thai baht and US dollar. So the question is, given this time series, this pattern of the exchange rate, can you predict? So this is the end of March 2011. Can you predict the exchange rate in the future, in April or in May? Okay. So if someone has a model, has a relationship that say like The price in April should depend on the price in March and Feb. And our goal is to, if I write it mathematically, it would be x hat at t plus 1 is sum a1 times x at t, right, plus a2 xt minus 1, because March is 1 step behind April and Feb is 2 steps behind April. So building a relationship would mean to come up with this mathematical equation. And of course, we're going to debate whether this model is good or not, right, by using the principle we learned here in this class. And we're going to learn about the method. Okay, if you believe that this model is structurally suitable, what are the base values of A1 and A2? Okay, once you have A1 and A2, of course, you can predict the future of stock price, future value of the, sorry, not stock price, exchange rate. Okay, this is a class of a prediction problem. Classification, a classical, conventional example, which is well known here, is the handwritten digit classifications. You have numbers 0 to 9. Okay, written by hand. You wanna feed this handwritten image, and you want to classify. All right, with this handwriting, is this what is this number? Is related application would mean like you have a post mails, right? And of course, people will write a zip code. All right, write a zip code. Somehow you want to have image that can be done by the camera or anything, like you feed all these post mail. And if you can detect, I mean, all you have is the image, right? And is there a way to detect what is the number so that you can sort the mail to different destinations? In this example, the class that we would like to detect would be 10 classes, right? Because those are 10 numbers from 0 to 9. The data are the images of 10 written digits. Model inference, as I said before, there can be many up to applications. I can give some examples here that suppose you have input and output variable. Okay, and somehow your statistical model can give you, like from the model parameter or some function of model parameter, somehow it can give you the structure of these dependence or the relationship. It would be quite it would be very interpretable that you can say more. For example, from this for this illustration, you see that the connection that I draw here is this is sparse. These are not full connections. What I can say, interpret or infer, is that my first component of the output y1 only depend on the first predictor, doesn't depends on other variables. This kind of thing. Okay. I have more related applications, like from brain analysis. This is brain images in 3 different views, and the sphere, the green spheres you see there, that that locates different brain regions. This is this is from the back, when you see from the back of your head. All right, this is on the top. This is on the side, okay, of the brain. The red links are the connection between 2 brain regions. This is an example of model inference that says, okay, the region A and B, all right, these have some connection. We believe that whatever activities occur in the B okay, can be affected by activities in A. All right. So these allow, like, what if we have this kind of brain network, it allows the neuroscientists to understand the functioning of the brain better, right? For example, for those patients who have symptoms, Alzheimer, Parkinson, right? Even though the Parkinson patient is very like mechanic, right? But it is known that it is caused by some part of the brain that is malfunction. Schizophrenia, these kind of thing. These kind of thing that people still explore what caused the problem in neuroscience field. So how can we have what make us to have this brain network? Of course, you have to build some statistical model, and you have to justify that when you say that there's a connection here, what do we mean by it mathematically, right? You may have heard of the name correlation matrix or those kind of things, but that one is a simple and basic way of saying relationship structure. Okay, we have more advanced and more statistical definitions of relationship. Okay, that we can explain as well in the class. I would say so when we see different problem objectives in statistical learning, I think I can summarize essential elements here into four modules. Okay, in order to 5 modules. Sorry. Of course, I hope everyone agree that in order to learn something, you need to have data. And this is probably one of the most difficult steps to get quality data from applications. Data scientists come up with a mathematical model to explain between y and x. Okay, data scientists also need to understand what kind of estimation technique in order to estimate this f. Okay, in order to come up with this math model, it's not just about applying some existing methods. If you have some more of prior knowledge, the better you know, the better you know about the application, the more interpretable meaning of the model you can get as well. For example, if you you have EEG, everyone know the EEG. EEG is an equipment to measure your brain signals, electrical signals. Someone can Google. So the EEG would be an equipment that it has probe, right, on your scalps, and it will measure electrical signal here. One probe will attach on your scalp, and you can design how many probes you would like to attach. Okay. And then if you have a question, for example, if you want to, for example, detect the seizures in patient seizures, then people who have some prior knowledge, which means people who know a lot about seizures, those are doctors, right? So doctors will have some fundamental background in this seizure symptom. For example, he would know that most of the seizures will occur in this frequency band, for example. Which means if you incorporate this prior knowledge, it will allow you to, once you have a signal in time domain, all right, if you want to filter or you want to get rid of some artifacts, these prior knowledge will make you a better decision to filter those noise because you don't want to corrupt the intrinsic signal from the EEG. Okay. Prior knowledge also help you to set up the experiment appropriately. For example, for those who work with the EEG, they know that the probe that attached on the forehead, all right, on the forehead here, it will be more corrupt by the eye blink signals. Whenever you blink, there's going to be some neuronal activities going on in your forehead area, which means the EEG on the channel that attached to the green one here, will likely to have more artifacts from the eye blink signals, and you need to get rid of those signals better. Okay, so what I'm saying is that prior knowledge about a certain application is very useful. You cannot just not all the models are good. All right, you can pick up some model, feed the data in, but what you get is just some performance. Those who have prior knowledge can interpret and adjust or improve the model in a better way. Last is the most one of the most important elements as well, is in order to estimate a model, most of the estimation problem is optimization. Okay, this is how you train, how you estimate the model parameter. Most of the time you need numerical methods. Okay, that can be like transform the signal in another domain. It could be a method on signal processing, or it can be tools in optimizations. Okay. If you focus more on developing a model, I would say all the pink ones are important, and these are the roles of data scientists to know. To obtain data, of course, to obtain data, that could be the role of a data engineer for those who take care of the physical infrastructure to obtain the data. Okay. If I need to refer about the related class, this is our class. Okay, we will take care of estimation, math model, and numerical methods. All right, we briefly talk about that as well, but not into deep details. We have optimization class this year, 598 spatial problem in EE. And last semester we have 505 intro to optimization. These will take care of numerical methods. For prior knowledge, it depends. All right, if you work on biomedical application, you take classes on those areas. If you work on time series, you need to know about random process, so things like that. Okay. All right. Are we settled with this like background and setting? Do you have questions? In a mathematical setting, when we talk from now on, when we talk about this class, the variable y is a response. Sometimes it's called dependent variable or a target. For classification, your y would be the label of the classes. Like binary classification is either 0 or 1, right? Or for the regression problem, your y probably is a real number. The variable x is the predictors, independent variable, or sometimes it's called features. The goal, as I said again, you believe that y, the response, has some relationship with the predictor by a nonlinear, typically nonlinear function f, plus some noise corrupted, so that what you measure, what you see in the variable y is random. Okay, we will now say that the whole point is to estimate f. Okay. This is what I explained before. Once you can estimate f, all right, it depends. You can perform classification, prediction, inference. Let me briefly talk about the approach. Okay, there are two types: parametric approach or model-based. These are the approach where you specifically come up with a structure with a mathematical equation of f. For example, f hat x is a linear function of x. F hat x is a logistic function of x. In this approach, once you can determine the mathematical description, you will see that the remaining problem is to estimate the model parameter. So basically, in this example, you choose beta 0 to beta p such that your f hat x approximate fx well. The model-based approach is known to, of course, have some more property. It involves a numerical method to solve. It also requires more samples to train the model as well. The other approach is non-parametric. Okay, it doesn't assume an explicit form of model. Okay, we say that we focus more in this class. We focus more on parametric approach. You see an elements in the statistical learning. If you look in a big picture, you will see that first of all, if you take a look in the aspect of learning objectives, there are classification problem, regression problem, or the prediction problem. Prediction or forecasting means that you want to predict the values of variable in the future. If you look from the aspect of learning methods, they can be supervised and unsupervised, right? Model-based or non-parametric, as I mentioned before, or it can be ensemble and non-ensembles. Ensemble model means that you have many models, many learners, and you would like to, for example, you have F1 hat, you have F2 hat, you have FK hats. You have kind of sub-models, and you want to integrate, aggregate the information of all those models to provide. There's going to be some ensemble step here that provide F hat X at the end. Okay. We can talk about this slightly when we discuss about tree-based methods. When we look at the data, okay, the data have different types. I'm going to go over that real quick. Some procedures involve the statistical learning. Okay, it starts with some pre-processing step that is unavoidable always. Removing artifacts, cleaning the data, impute the missing data, right? The second example, sometimes you need to transform the data in another domain. Frequency domain is the most common one, all right? Extract some features. What I can explain is that suppose you have a time series signal YT, okay. EEG signal, to be precise, is a time series signal. From my prior knowledge, for example, that you know that things that can explain seizures is actually hidden or I mean stored in this energy band. In this energy band, this is frequency domain, which means you need to take Fourier transform into the frequency domain and focus on this period. All right, but then on the frequency domain, what is the variable that you want to present the energy in this band? Sometimes you need to compute what? Sometimes you compute the energy, right? Which is the area under curve of the spectrum. Okay, or you can some example is the transform step is to take the wavelet transform, and the feature would be wavelet coefficient. Okay, because you believe that the wavelet coefficients can explain the response variable. These in the future, there will be a short course on the wavelet transform. Okay, and important steps in statistical learning is model training. In other words, this is the estimation step, and this is what we focus here. Okay, model validation is to kind of a checklist to evaluate the model that we just trained, whether it's good enough for this application. And the last procedure is, once you get a model, can you infer to some other questions? All right. So far, do we have questions? Bhumipat, you have questions?
No, Ajahn.
I'm reading the question from Hannah. Is underfeeding is more severe problem than the overfeeding? The underfeeding is more severe in regression. I read this from econometric textbooks, but on the other hand, stat learning seems focused on overfeeding due to the bias variant herself. To explain underfeeding and overfeeding, which one is more severe, or I mean, it depends on the model. It depends on the model. In some applications, the relationship, this is a point where I mentioned that the more you know about the prior knowledge, the better you can assess, evaluate the model. Some application, I would say, if I go back here, in this solar application, the data are very well behaved. It almost corresponds to the physical relationship. Like if we derive some equation that explains solar power, between solar power and solar irradiance from electrical circuit, you will see that it can be approximate well with a linear function, which means in a simple model like linear regression, we don't have the underfitting for this application. This is to answer Panat. We cannot say in general, Panat. It depends on application, depends on the model. Of course, in this application, it looked ridiculous to use deep learning model to just explain between solar power and irradiance, and you're gonna get an overfitting problem. On the other hand, if you work on a very complex complex system like the brain dynamics are very complicated. So as of now, of course, people have tested using many things, and most of the time, simple model cannot explain well with the brain, cannot explain the brain dynamics well. Which means for brain application, of course, we will see some concern in the sense of underfitting if you still use simple model. Okay, I think we have some time left. I would like to let me mention about some data types that you're gonna encounter with this class. All right. First of all, we look at the if I category into broad groups first, is going to be quantitative versus qualitative data. All right. Or numerical data. Okay. So numerical data also can be split into four For groups, cross-section, time series, panel, repeated. Let me explain just by you know, this illustration. Okay, you want to study about kid obesity, okay, by measuring his height, his weight, his waist, all right? And let's say you want to study on population from different regions. You have Bangkok, you have northern kids, and you have southern kids. They look pretty different, right? Okay. First of all, I have some problem with my screen, so I'm gonna carefully zoom in. All right. if if I observe subjects from 3 regions, you know, 3 subjects at a certain time, at a fixed time, this is called cross-section. All right. I have kids from like many cities. I observed it in 2017. Bunch of kids here. So this is cross-section. If I go back to the context of random variable, so kid, what do we call this? Like remember that the randomness occur in the sense that because all these kids have different profiles, right? So you can think of like when you measure the height and the weight of one kid, you get one value, and you observe another sample of the kid, you get another value. So when we think about like these data, we can treat them as random. Okay. But because you have data from 3 regions, okay, you observe it at a certain time. So kid, that is a scalar random variable or vector or time series.
I think it's a scalar.
Not scalar anymore, because I can say my y, right? My y1, y2, y3. My y1 is the data from, is the value from, for example, the height of Bangkok kids. Y2 is northern kids, y3 is southern kids. But because I observe it at a fixed time, all right? Many samples means many subjects, many kids. So cross-section is actually random vector. In the context when we discuss about, you know, random variable, random vector, random process. All right, random vector. Next. I observe the Bangkok kids, you know, did in this group, but I observe it over time. All right, I observe it over time. This is called time series. All right. And it is a scalar time series. In the context of random process, we can regard this as a random process as well. Okay, because you believe that you know, there's some dynamic, some temporal dynamics of you know, the profile of these kids over year. Now, next one. If you observe on different regions of the kids and also that at different times, this is called panel data. And if I use this term, it would be the same. Is multivariate time series, because my YT is, my Y is Y1T, Y2T, Y3T. My 1T is a profile of Bangkok kids. My Y2T is the profile time series of the northern kid, and Y3 is the southern kid. All right. I mean, I just mentioned the names that people call it probably differently in different fields. All right, cross section, time series, panel. These are the terms used most in econometric, but panel data is basically multivariate time series. EEG, as I explained earlier, you observe electrical signal on many probes. And these signals are observed over time. So EEG signal is multivariate time series. While one would be electrical EEG signal on channel 1, on probe 1, for example. There's going to be some detail about this equipment as well, because there's going to be a reference point, and actually what you observe is the potential difference between one probe and the reference, for example. But please go through that application. Okay. Last, another type of data group. This is called repeated cross-section. What is it? It means you observe kids from each group. For example, here I observe a kid from in Bangkok, but I observe it over time. But remember that the kid from 2017, for example, what's the name? Okay, this kid names Tom, right? Named Tom. By 2018, like, of course, Tom here in 2017, he's 6 years old. By 2018, he's going to be 7 years old, right? In this type of study, you want to control. For example, you want to control that. Oh, you want to explore about the kid obesity at 6 years old. Okay, which means when you observe at 2018, Tom is no longer in this study. We're gonna observe another kid named John instead. John is 6 years old in 2018. Okay, so this is called repeated cross-section. You observe each group, but actually different individual. Okay. All right. These are the quantitative data. Okay, for qualitative, these data are non-numerical. Okay, most of the time assumed to be in a finite set. Otherwise, it's difficult and maybe involve a lot more. In a finite set means that the members in the set is a finite. For example, you have the class of the states as Bangkok, you know, these three cities. You have patients. You want to assess the condition. You have a COVID-19 or not. So the outcome would be negative or positive. All right. These are qualitative data, non-numerical. Some other names are categorical, discrete, or sometimes it's called factors. The thing is, it can be represented by numerical codes that you can, there's a way to map, all right? There's a way to map this label into numerical vector. The easiest one to explain is for two outcomes, you can use 0 to label negative, and you can use 1, like numerical code, to label positive. All right. Ordered categorical data. Okay, these are qualitative data with some ordering. It has a sense of ordering, but the scale is not clear. For example, small, medium, or large. Like it had a sense of, oh, small is of course smaller than medium, right? Something like and you have health condition of mild, moderate, right, and severe. This has a sense of the degree of severity of a symptom, but it doesn't have an appropriate scale to measure. So this is called ordered categorical data. All right. I explain more. Okay. Next is features. Feature is an input variable that explains the response. Sometimes feature is an input variable that is relevant, right? That must be relevant. But in many cases, the selected variables in the model are not actually relevant, or it doesn't highly affect the variable. So that's why they have a process called feature selection. Okay, you want to select Y that mostly explain why. These process can be can be explained from the concept that if the response if the variable X for example is not correlated with Y at all, why would you want to include X in the model, right? Go back to the what else? Maybe go back to the solar power application. Okay, all I listed there would be the weather variable, the irradiance, right? If someone say, why don't you put X? Why don't you include? Why don't you include? What should say? Why don't you include? So think about something. Why don't you include? Probably relative humidity. Okay. I put this one. I initially say that is a factor, is influence variable, but I'm gonna let you explore this matter as well. From my previous studies, I saw that the relative humidity, when I compute the correlation with Y with the solar power, it had less correlation compared to other weather variables. So it means that, probably relative humidity is less relevant to Y. And in the step of feature selection, okay, which mean or variable selection, whatever you can call it, it should be a process that you select only the most relevant variable to explain why. Feature extraction is a process of transform the raw data into another domain, like for example, wavelet or frequency domain. Okay, there can be other methods, related methods that you might have heard of the name also, PCA, ICA, independent component analysis. Okay, this will be taught by Ajahn Shanchai in the third part of the lecture. Okay. I think I'm going to stop here. Otherwise, it would be more. Okay, I'm going to stop here and then open for questions.